What we're going to cover in this section is now we've talked about partial derivatives, and those are with respect to x and with respect to y. So those give you the slope of the tangent line in those directions. What happens now if we want the rate of change in a different direction? So maybe in some terms of some arbitrary vector instead. So it's going to take us a little bit of a while to build this concept, but it is important that you see where this comes from. So ultimately what we're going to do is we're going to start with what do our normal partial derivatives look like, and then how can I change it so that maybe I'm not changing one component, but I'm changing both of them instead. And it'll lead into this idea that's called a gradient vector. And that's going to be one of our main components really throughout the end of the semester. So to begin, we're going to refresh on what those partial derivatives formally represent. So we've seen for a function z, which is a function of two variables, x and y, the partial derivatives being the partial of f with respect to x, and I'm specifically going to look at a certain point, can be defined by a limit. So that's the limit as h tends to 0, and it's just like our standard limit definition of a derivative in Calc 1. It's f of x naught plus h, y doesn't change, and then minus f of x all over h. And then in the analogous way, the partial derivative of f with respect to y, specifically at some point, all that's doing is changing the x and y to whatever those values are of the point, is exactly the same thing, but now you're going to add that h into the y component instead. So x is completely untouched, and we have that change in y instead. And then it's all over h. So these two limits and these two partial derivatives just represent the rate of change of z in the x and y directions. Respectively. At some specific point, which in this case is x naught, y naught, and then whatever the z value is. So you would plug that into the function to find the z value. So instead, a different way we can think about these is it's the rate of change in the directions of the I and j vectors. Remember, I is in the x direction, j is in the y direction. So that's a second perspective on this same thing. So alternatively, these are the rates of change in the directions of I and j. So what I want to do now is, instead of looking at the I and j vector, we're going to consider any unit vector, and unit is important here. So we're going to try to build what if we want to find a rate of change of z in the direction of an arbitrary unit vector. which which again, I'll call U, and it has some components A and B. But the key, oh, let me change my tool to a nicer size. It has to be a unit vector. Okay. So the way you can kind of think about this is maybe your surface represents like some kind of like area where you're going to build a road. Well, if you need your road to go in a specific direction, you need to guarantee that in that direction, the steepness isn't too much, because that's not good for your car. So directional derivative will kind of give you an idea as to what's the steepness there and if it's something that's suitable for the car to get through. So what I want to do is, the problem is it's a little bit harder because now both of these components are changing, because it's not just I or J. So I'm moving in both of these pieces. And with doing that, I can't really do a 2-variable limit. Like, I don't want X and Y to both be approaching these particular values. So instead, we're going to try to build this and condense it to a single variable limit too, just dealing with H. And then we're going to see, does maybe something else pop up, maybe utilizing our chain rule, that will make this derivative easier to calculate, because we definitely do not want to go through a limit definition to calculate a derivative. So we're going to go ahead and we're going to try to draw a nice picture to really set the idea of what's going on. So we've got this point x naught, y naught, and then the z component. And we're looking at that point in a particular direction, and we're trying to basically determine, how is this function changing? Is it dropping a lot? Is it climbing a lot? Or is it kind of staying flat at this point? So what we're going to do is we're going to consider the vector through the point, which is that initial point, x naught, y naught. And I'm specifically going to look in the xy plane. And some arbitrary point, x naught, xy, 0. That's parallel to u. So I'm going to do my best to draw this as clear as possible, and then we're going to see, can I figure out what's going on. So here is our 3-dimensional system. This is the x, this is the y, this is the z. And so I've got some surface going on here. I don't know, maybe it looks something like this. Easy surface to draw. And what I've got going on is I've got this point here, which is where I'm trying to look at the rate of change of specifically. So this is the point x naught, y naught, and then the z value, which is just plug in those xy values into the function. Okay. So I'm trying to see in some direction u, what is the rate of change at this point. So I'm going to go ahead and I'm going to see if I drop this down to the xy plane. Maybe it lands right here. That would be the projection onto the xy plane. So this would be the point x naught, y naught, 0. And I'm trying to find the rate of change in the direction of some unit vector u. So here is u. Okay. This has components a and b. Right. So I can actually draw a right triangle in now based off of these. So I have this side that runs parallel to the x-axis, and this side that runs parallel to the y. And although it doesn't quite look like a right triangle, it's because we've got that forced perspective going on. It is one. So this side length would be a, this side length would be, and this side length would be the magnitude of a squared plus b squared under square root. So what I'm doing is I'm instead going to try to see, how can I figure out this rate of change? Because again, it's going to require me having some point that I approach this particular one in the direction of u. So this is where that other vector comes into play. So what I've got is this other point right up here. And this vector is going to run parallel to our vector u. Okay? So if I were to look at the projection of that onto here, it would maybe look something like this. So this point we're going to be letting change. It's got components x, y, and then again the z values corresponding to it. And essentially we want to see if we let the difference between these two approach 0, what does that go to? But the problem is I would have to let x approach x naught, and I would have to let y approach y naught. And that would be a very difficult limit to compute. So what I want to see is if I'm letting these 2 points approach each other, is there a different way I can talk about that limit in terms of a single variable? And it's going to depend on this vector u, okay? So what we're going to do within here, this point at the end of this would be x, y, 0. So again, that projection, just dropping it right down. I can create a mini triangle within here. So I've got a mini right triangle that looks something like this. Okay. I have 0 idea what these side lengths are. However, these are 2 similar triangles because they're right triangles and they share an angle. So really the sides are just scaled up versions of these sides. So I have no idea what these side lengths are. However, I know it's some scalar multiple of side B. So I'm going to call this side HB. And in the same way, this side right here would be H times A because both the sides of the triangle have been scaled down. And this vector is going to be our vector H, which has components HA and HB. Okay? So what ends up happening, do this over to the side, is the vector H is found by taking the difference in these 2 points. So it is x minus x naught, y minus y naught, and 0. But all that ends up becoming is some constant times A, some constant times B, and 0. Okay. So what I'm actually able to do is I'm able to say these 2 components are equal to each other. So x minus x naught is HA, which ultimately means this x component of my thing that's changing can be written as x naught plus some scalar multiple times A. So this is that unknown variable that I'm trying to let approach 0 because it's the distance between my 2 points. And that's what I want to calculate a derivative. And then in exactly the same way, y minus y naught is h times b. So our y coordinate can be written as y naught plus hb. X naught, y naught is the initial point. That's a given constant. AB is the directional vector that I'm trying to find the rate of change in. Those are given constants. So what this ultimately does is it makes it so that I can take a single limit as h approaches 0 to let these 2 vectors approach each other. So this is how we define our directional derivative in terms of a single variable. So to tie all of this together now, we define the directional derivative of f at the point x naught, y naught in the direction of a unit vector u which has components a, b as the following. Okay. I'm going to write the limit first, and then I'll show you the notation that we use for it. So it becomes the limit as h approaches 0, and we have a giant fraction, and we're just letting h go to 0. In the top component, we have x naught plus ah, or you can do ha, either one, and then y naught plus hb, and then minus that initial point. Okay. So it's pretty analogous to our normal partial derivatives, but instead of just one component changing, they both are. And we've had to scale this component h into those directions a and b. So this is how we define our directional derivative, and the notation that we're going to use is we're saying take the derivative in the direction of u of the function at the point x naught, y naught. And then of course that's provided this limit exists. So this is the formal definition for the directional derivative. However, in practice, you definitely cannot compute this. It would be very difficult and tedious to go through. So in the case that the directional vector is not I or j, because all that would do, to just kind of show you, if our vector u was 1, 0, that would be I. So this would be gone, and then this would just be h, exactly our derivative, our partial derivative with respect to x. And then likewise, if I switch these around, if it's 0, 1, that's j. So 0 for a would make this disappear, and then that part would just be h, exactly the partial with respect to y. Okay. So this is just a more general derivative or rate of change. Right? But again, very, very, very difficult to compute. So we're going to try to come up with something else. So this limit is difficult to compute. If the unit vector u is not I or j. So we need a better way to compute a directional derivative. So what I'm going to do is kind of show you how the chain rule comes into effect, and it makes us evaluate something that's a little bit easier. Okay. So if you notice this expression here, again, the only variable is h. X naught, y naught, fixed point, a, b, fixed components of a vector. So what I'm going to do is I'm going to define g of h to be exactly that first component. Okay? Because h is the only variable. Then what I can actually do is if I go through my Calc 1 definition for g prime of 0, this is the limit as h tends to 0 of g of 0 plus h minus g of 0 all over h. Okay. Well, all that really becomes g of 0 plus h is just g of h minus g of 0 over h. Okay. And so filling in the pieces based on this definition, g of h is exactly this expression. So this is f of x naught plus ah, y naught plus bh, and then g of 0 would be, I replace h by 0, so both of those pieces would disappear, and that would be f of x naught, y naught, all over h. And that is exactly the directional derivative at this particular point. Okay. So if I can come up with a different way to calculate g prime of 0 based on this expression, that is my directional derivative. So it gives me a different way to calculate it. Okay. So what I'm going to do is I'm going to utilize, went a little too far. I'm going to utilize this expression, and I'm going to go ahead and I'm going to try to see if I can rewrite g prime using my chain rule. So ultimately, g of h, we evaluated at a specific point. It is a function of x and y, okay? Where specifically, I can say the x component is x naught plus ah, and the y component is y naught plus bh. Okay. So thinking of our chain rule diagram, we've got g up here. It depends on the variables x and y, but then ultimately these two just depend on that single variable h. So by chain rule, we get the following. If I'm looking for g prime of h, because I've got the single variable dependence, instead I'm going to do one of two things. I'm going to go through x to get to h. So this would be the partial of g with respect to x. And then I would take the derivative of x with respect to h. Or I can go down the other path. So I can go through y and then to h. So likewise, I add the partial of g with respect to y, and then the derivative of y with respect to h. Okay. So figuring out what each of these pieces are, well, g is just f of xy, so the partial of g with respect to x is the partial of f with respect to x. And then likewise, this is really just the partial with respect to y, because again, g, we're saying is a function of x and y. Okay. Now these other two pieces, we're going to go back to this definition right here. If I take the derivative of this with respect to h, well, h is just this component here, so the derivative is just a. And then likewise, if I take the derivative of this with respect to h, well, this is the only h piece, so that derivative is b. Okay. And so what I can actually do now is we can write this in terms of vectors, because you see we've got AB, which is our unit vector u. Okay. And since I've got something times something plus something times something, that's just the dot product. So this is the partial with respect to x, the partial with respect to y, dot product with a and b. Okay, because again, you would just multiply the like components, add them together. So really this is taking a vector with the partial derivatives and dot producting it with the vector u. Okay. So this is really amazing for us, okay? So ultimately, again, just to give you a little bit of a picture as to what's going on here, do this right here. Here is our function z. We're looking maybe at a specific point right here, and I've given some vector u, which is unit. The directional derivative will point in that same direction. Okay. So this vector is super important for us. If our vector u is I or j, that would be like 1, 0. Well, that would just give you the partial with respect to x. If it was the vector j, this would be 0, 1. So when you take the dot product, it gives you the partial with respect to y. So this vector, you're going to see, is going to pop up a lot of times. This is called the gradient of our vector f. So the gradient of f is defined by the following. Okay. We're going to use an upside down triangle with a vector notation over it, acting on the function which has two components, x and y. So this creates a vector whose components are the partial derivatives. Or you can also do this if you have a triple, if you're taking the gradient of a function that has components x, y, and z. This would create a triple vector whose components are still partial derivatives with respect to each of those variables. So all of this work, I still haven't gotten to how to actually calculate this directional derivative. But however, remember g prime of 0 is exactly the directional derivative. So if I just plug 0 into this expression, that will give me my directional derivative. Well, when I go ahead and plug 0 in for these things, all it does is give me my x and x naught, y naught. So this last little bit is going to tie it all together, and in practice, calculating the directional derivative is really not that bad. So as a final tie-in, we know g prime of h is going to be this gradient vector dot product with u. Okay. And then based on our expression for g, this is the partial with respect to x, and those components are exactly way back up here. So we would evaluate this at x naught plus AH, y naught plus BH. And then same thing in the second component. It would be x naught plus AH, y naught plus BH. And then this is dot product with the vector u. Okay. But g prime of 0 is exactly our directional derivative that we're searching for at that point. Okay. So if I plug in 0 for h, all that does is it makes all of these pieces disappear. Okay. So what that gives us is the directional derivative we're searching for at this particular point is going to be the vector, which has the partial with respect to x, evaluated at x naught, y naught, the partial with respect to y, evaluated at that initial point, and then dot product with u. So really, the directional derivative of a function at a specific point in the direction of u is going to be the gradient vector of a function evaluated at the point you want, dot product with u, as long as u is a unit vector. Okay. So this is going to be how we can actually calculate a directional derivative. Okay. So a lot of work to get to this point. But again, it's important that you see where this comes from instead of just accepting it at face value, because this gradient vector is going to be important and it pops up in a lot of things. So you need to see where it pops up at. But now that we've built this, we can go ahead and we can actually calculate some directional derivatives. So let's try a few examples. Let's find the directional derivative of the function f, which is e to the x sine of y, at the point 0 pi over 3 in the direction of b. Which has components -6, 8. So first thing I'm going to do is I'm going to go ahead and find this gradient vector, and then I'm going to evaluate it at this specific point. So starting with our function, we need to find the partial with respect to x, and we need to find the partial with respect to y. So if I find the partial with respect to x, sine of y is just a constant. Derivative of e to the x is e to the x. So the partial with respect to x is e to the x sine of y. When I take the partial with respect to y, this is a constant. Derivative of sine of y is cosine of y. So my partial with respect to y is e to the x cosine of y. So my gradient vector is going to be e to the x sine of y, e to the x cosine of y. And specifically, I'm going to find the directional derivative at the point 0 pi over 3. So I'm going to plug this in. X gets changed, or x gets evaluated at 0, and then y gets evaluated at pi over 3. So we end up with this vector. Okay. E to the 0 is 1. And then if you think of pi over 3, that's your 60-degree angle. So sine of pi over 3 is going to end up being root 3 over 2. Cosine of pi over 3 is a half. Okay. So I have found this first component in calculating my directional derivative. Now the second thing I need to do is I need to dot product this with u. However, the vector I'm given is not a unit vector. So before we can actually take our dot product, we need v to have length 1. But currently it doesn't. So what I want to do is I need to find a unit vector that's in the same direction as v. So all we do to find that unit vector is we take v and we divide it by its length. And so v is negative 6/8, just to refresh back up here. And then I want to divide it by the length of this vector. So that means we need to take the square root of each component squared. First component squared is 36, second component squared is 64. So this ends up being negative 6/8 over 36 plus 64 is 100. So that square root is 10. So the first component would be negative 6 over 10, which I'm going to simplify to just not have as big a numbers. That's negative 3/5. 8 over 10 is 4/5. Okay. So we have our gradient vector at that specific point. We have our direction vector that is unit. I'm just going to dot product these two to find the directional derivative. So the directional derivative is the following. So our derivative in the direction of u of f at the point 0 pi over 3 is exactly the gradient vector of f at that point, dot product with this unit vector u. So we take root 3 over 2 1/2, and we dot product it with negative 3/5, 4/5. And so I just need to calculate that. Again, to take a dot product, you multiply the like components, and then you add them together. So this will be root 3 over 2 times negative 3/5 plus 1/2 times 4/5. Okay. So that will be negative 3 root 3 over 10 plus 4 over 10. And so you can write this as a single fraction. It would be the numerators added together. So I'm going to put the positive one first over that common denominator of 10. So this is the rate of change of f at the point 0, 3 in the direction of u, which is the same direction as v. Okay. Let's try a second one of these. We're going to find the directional derivative of f. Which is the function y(e) to the negative x at the point 0, 4 in the direction of theta, which is 2 pi over 3. Okay. So the problem here is they have not given me the vector. They've just told me in the direction of a specific angle. But if you think about that, it's just a two-dimensional vector. So if we have our xy plane, 2 pi over 3 is back here in quadrant 2. So this angle would be 120 degrees. Okay. And I'm looking for this vector to have length 1. So this would be u. Since it's a unit vector, it's going to lie on the unit circle. So those endpoints really are just going to respond to cosine of theta, sine of theta. Okay. So the vector u that we're looking in the direction of has components cosine of 2 pi over 3, sine of 2 pi over 3. And again, pi over 3 is a 60-degree angle. We are in quadrant 2, so that means the x is negative. So this first component is negative 1/2. The second component is positive. It is root 3 over 2. So this is my unit vector u. Then what I need to figure out what is the partial of each component evaluated at that point to get me my gradient vector. So if I look at f of xy, it's y e to the negative x. So the partial with respect to x would be the y stays put. Derivative of e to the negative x is e to the negative x, and the minus pops out. So this is negative y e to the x. The partial with respect to y, well, derivative of that is 1, so the e to the negative x stays attached. So my gradient vector is going to be negative y e to the negative x, e to the negative x. And then evaluating this at the point 0, 4, y gets replaced by 4, x gets replaced by 0. So this ends up just being negative 4, 1. So I have my gradient at that point. I have my direction vector. So I can figure out that the rate of change of the function f in the direction of u at the point 0, 4 is just the dot product of these two. So I'm going to take the vector negative 4, 1, and I'm going to dot product it with u, which is negative 1/2 root 3 over 2. So multiplying the first pieces, negative 4 times negative 1/2 gives us positive 2. And then moving on to those second pieces, 1 times root 3 over 2 is just root 3 over 2. And then I can leave it just like this. This is the rate of change of f at the point 0, 3 in the direction of the angle 2 pi over 3. So the last thing I'm going to do with this directional derivative is talk about how can you find the maximum value of the directional derivative and in what direction does that occur. Okay. So I'm going to give you the theorem and we're going to prove this result. So suppose we have f is a differentiable function. Then the maximum value of the directional derivative of this function is going to be the magnitude of the gradient vector. Okay. So no matter what, that is the absolute max rate of change, the magnitude of the gradient. And the direction it will occur in is going to be the exact same direction as the gradient vector. So, and it occurs, I could spell that word, occurs when u is in the same direction as the gradient vector. Okay. Because if you think really back up here, I've got my gradient vector. I could go ahead and dot product it with whatever vector u. That would give me a function of 2 variables. So what I'm asking is what is the absolute maximum z value that function has? And that's going to occur specifically when the vector u points in the same direction as the gradient vector. And the absolute max value is going to be the magnitude of this vector, okay? So this proof is actually really simple. It is one line, and that one line tells us everything. So if I look at my definition that we've come up with for our directional derivative of f, it is the dot product between these two vectors. But remember, our dot product relates to the angle between these two vectors. So I'm going to rewrite this based on the angle. So this is also equal to the magnitude of the gradient vector times the magnitude of u times cosine of the angle between them. Okay? But the magnitude of u is just 1 because u is a unit vector. So really our directional derivative is the magnitude of f times cosine of theta. Okay? Where theta is the angle between the gradient vector and u. Okay. And so if you think about this expression, the most the cosine function will ever be is 1. So at most, this directional derivative is the magnitude of the gradient vector. When it equals that maximum, it means that cosine of theta has to equal 1 exactly. So the value of theta is 0. That means the angle between the gradient vector and u is 0. So they point in the same direction. So this one line tells us everything we need to know. And just to summarize that last part, so the directional derivative is equal to the maximum value when cosine of theta equals 1. So ultimately, theta has to equal 0. So from this, the maximum value is indeed the magnitude of the gradient vector, and it occurs when u is in the same direction as the gradient vector. Okay? So you don't have to do a ton of work to find the maximum. It is just going to depend on the gradient vector. Okay? So I'll give you an example utilizing this. We are going to find the maximum rate of change of the function, which is going to be a function of x, y, and z, of x plus y divided by z, at the point 1, 1, negative 1. And we want to find the direction in which it occurs. Okay. So I need to find the gradient vector, and that's going to tell me everything. But if I've got to take 3 partials, I definitely want to rewrite this a little bit to make my partials easy. So our function is x plus y over z. You can write this as x plus y, z to the negative 1, to make my partial with respect to z easier. And then to take my partials with respect to x and y, let's just go ahead and split that fraction. That is x over z plus y over z. So if I want to find the partial with respect to x, this is the only thing that deals with x. Derivative of x is 1. So this partial will just be 1 over z. And likewise, the partial with respect to y, if I take the derivative of this piece, it's 1 over z. And then my partial with respect to z is where I'm going to go back to use this. The x plus y is a constant. Derivative of z, the -1, has the negative pop down. You'd increase that power, and it would be z to the -2. So this ends up being negative x plus y over z squared. So our gradient vector is just those partials in order. So that is 1 over z, 1 over z, and then negative x plus y over z squared. Okay. So I specifically want to look at the maximum rate of change at the point 1, 1, -1. So I'm going to go ahead and evaluate the gradient vector at that point. So the first component is 1 over z, so that's 1 over -1. First component is -1. Second component is the same thing. If I plug in 1, 1 here, that would give me 2. -1 squared is 1. So overall, this is -2. Okay. So the maximum rate of change is just the magnitude of this vector. So that would be -1 squared, -1 squared, -2 squared under a square root. So the absolute maximum rate of change at this specific point is going to be √6. And the direction in which it occurs is exactly this vector. So max rate of change is √6, and the direction is going to be this vector. You can make it a unit, but again, it's just asking for the direction. It doesn't say it needs to be a unit. So the last thing we're going to do is we're going to see one more application of this gradient vector. And this idea is actually one of the most important things to us. So we're going to see a nice property that happens with this. Okay. So we're going to talk about tangent planes to level surfaces. Because we know the idea of tangency is super important. Now we're going to talk about if I have this surface or a level surface. So basically you have your function is equal to some constant k. Can I figure out a plane that is tangent at a specific point? So we're going to consider the surface which is we have a function of x, y, and z, which ultimately equals some constant k. And we're going to let x naught, y naught, z naught be a point on that surface. Remember, when we're finding the equation of a plane, we need a point and we need a normal vector. So specifically, I'm looking at this point and I want to figure out what is a vector that's normal. Because as soon as I have that, remember the equation of our plane is that a component of the normal vector, x minus the initial point. B component of the normal vector, y minus the initial point. And then c component of the normal vector, and then z minus the initial point ends up equaling 0. Okay? So I have these pieces, and I want to see what are the components of my normal vector. What is A, B, and C? And we want to see if I have this function, can I figure out those components easily? So we're going to do something a little bit different. I need to find a vector that is going to be orthogonal to my plane, which really means that my normal vector has to be orthogonal to my surface at that point. So I'm going to define the function r of t to have components x of t, y of t, z of t. This is going to be a curve, any curve, on the surface that goes through this point I'm looking at, where I'm trying to find my normal vector. So I'm going to give you a picture as to what's going on here to hopefully make this a little bit easier. Should probably, let me do this a little differently. Let me make my Z component a little bit longer. I keep making that a little too short. Rather these be shorter. I like to draw the same picture every single time for my level surface because it's a nice surface, it's not muddled. And so we've got this function of x, y, and z equaling some constant k. Okay. What I'm looking for at this specific point is I want to see what is a normal vector here. So n. So the components of this point, just so I don't mess up my picture too much, would be x naught, y naught, and z naught. So in this plane, it would be 0. So what I'm doing is I need to find this normal vector. I'm considering this vector function r of t that goes through this point and it lies on my surface. Okay. It can be any function that goes through that particular point. Okay. Because by doing this, what I'm able to say is if I look at the derivative at this particular point, this would be r prime of t, specifically at the point t0, okay, to correspond to the point x naught, y naught, z naught. Since this is on my point and this vector function r lies in the surface itself, I immediately know that these two are going to be orthogonal to each other, okay? Because this is tangent to the surface, and then this is that normal vector that points upward. And so my goal is to figure out what is this tangent plane at this particular point. Okay. So I know r prime of t is going to be in that tangent plane because it is a tangent vector. And I know n is going to be normal to the plane, okay? So I'm gonna actually see something really nice pop up as a result of this. So on this curve, r of t, we have the following. We've got the surface, f of x, y, z equals some constant k. But what I'm doing is I'm specifically looking at the function f, but I'm looking at this vector function inside of the surface. Okay. So really, I'm just parametrizing each of these components by x of t, y of t, and z of t to give me what does this vector function look like on the surface. Okay. And so if you look at this piece, what I can go ahead and do is take the derivative on both sides with respect to 0. Okay. So I need a little bit more room to do this, so I'm going to go down here. So if I take the derivative on t, derivative with respect to t on both sides, at least over here, derivative of this will be 0 because it's just a constant. And then if I want to take this derivative, I've got functions inside functions. I'm doing my chain rule. So you can think about drawing your tree diagram. F depends on x, y, z, and then each of these depend on t. So if I'm taking the derivative with respect to t, I'm first starting with f and going through x, and then I'm taking the derivative of x with respect to t. And then we've got to go through y, derivative of y with respect to t. And then finally z, and then the derivative of z with respect to t. And so this thing ends up equaling 0. Well, I can reverse engineer this. This is the vector, which has the partials. Partial of f with respect to x, partial of f with respect to y, and then with respect to z. Dot product with this vector ends up equaling 0. Okay. Well, the first component is just the gradient of this level surface. And then the second component is the derivative of r. So this dot product is equal to 0. So what that ends up telling me is this vector r prime of t dot product with the gradient vector is 0. Well, if the dot product is 0, remember that means they're orthogonal to each other. So this normal vector that I'm actually searching for is just the gradient vector of this surface. So this ends up being the gradient of f. Okay. So all this does is it tells us is in particular the gradient of f at this point where I'm trying to find the tangent plane, dot product with the derivative at that specific point, which again is still just x naught, y naught, z naught, is equal to 0. So the gradient vector at that particular point is normal to the tangent plane. At the specific point we're looking for. Okay. Because this vector is going to lie in the tangent plane because we know r prime is going to be tangent to the point x naught, y naught, z naught. So it's going to lie in the tangent plane. So if I'm looking for the normal vector of a tangent plane, it's just going to deal with the gradient vector. The gradient vector is normal to our surface. So what we can say is as long as the gradient vector is not the 0 vector, we define the tangent plane to the level surface, f of xyz equaling some constant k at some point to be the following. We would take the gradient vector evaluated at that specific point and dot product it with the vector x minus x naught, y minus y naught, z minus z naught, and these two will equal 0. So really all that means is the components in front of x minus x naught, y minus y naught, z minus z naught are going to be the partial derivatives evaluated at those points. So the first piece is the partial with respect to x, evaluated at that point, times x minus x naught. Then the partial with respect to y at that specific point, times y minus y naught. And then finally, the partial with respect to z at that particular point, times z minus z naught equals 0. And it's exactly the equation of a plane that we're used to. Which we found by this. So x naught, y naught, z naught are the point it goes through, and then a, b, and c were part of that normal vector n. It just so happens to be that our normal vector in this case is just the gradient vector at that particular point. Okay, so I'm going to omit doing an example of this just again so this video is not 2 hours long. But all you would do to find the tangent plane is find the gradient vector, plug in the point you're looking for the tangent plane for, and then those are the components of the normal vector you need to create the equation of the plane. We are going to talk about this more thoroughly in another video, so you can also utilize that to help you out. But really it's just a nice application that gradient vector is going to be orthogonal to our surface, which is a fantastic property.